The last part of Chapter 5 has to do with collecting light using telescopes. So the goals are: how do telescopes help us learn about the universe, and why do we put telescopes into space? Telescopes collect more light than our eyes are capable of. And of course, the larger the mirror or the lens, whatever we're using to collect the light, it's going to be much, much larger than our eyes are. Telescopes can also see more detail than our eyes, and that's called angular resolution, as we'll see in a minute. So telescopes can detect light that's invisible to our eyes. It can also discern smaller objects farther away, and it can collect light over a larger period of time. So telescopes are obviously much better than our eyes would be just looking through a telescope or a pair of binoculars. Bigger is better in the case of telescopes. Generally, a mirror or a lens, whatever is used, has a very large light collecting area and better angular resolution. And in the case of this particular telescope, there's two telescopes which can be used to combine the images into an even better image. This is a refracting telescope, a telescope that uses lenses, pieces of glass that are clear and shaped in such a way that they will focus the light, whatever it's collecting. So as you can see, there is a lens at the top of this telescope which brings the light down into the eyepiece, which puts it into focus for the observer, or in many cases a camera of some sort. So a refracting telescope, refracting means to bend, uses lenses to form the image, and you can see the picture of the telescope there. That's at Yerkes Observatory up in Williams Bay, Wisconsin, which is just within a couple hours of the Chicago area. So that's what we're looking at the top of page 122. This is a reflecting telescope, or reflector, some people would call it. That's at the top of page 123. It uses mirrors to collect the light, but it does so in such a way that the light comes into the tube, bounces off the primary mirror, which is at the bottom, as you see in the lower right, reflects up to the secondary mirror, and from the secondary mirror comes down into focus through the hole in the primary mirror. Now, these can obviously be made much, much larger. This particular telescope has 8 times the diameter of the reflecting telescope at Yerkes Observatory. And this is a good example of the size of some of the mirrors that are being made to put into these observatories. You can see the person there in the middle of the picture. On page 123 is the same picture. A nice place to construct an observatory would be at the top of a mountain where there's clear, dry air, so there's very little interruption of the image, less pollution, of course, and better visibility overall. This is in Hawaii. This is a different type of telescope, as you see at the top of page 124. This is a radio telescope in Arecibo, Puerto Rico. The dish at the bottom is actually occupying kind of a valley here. It's so large. These kinds of telescopes, radio telescopes, are collecting radio waves. Radio waves have a longer wavelength, so the telescope itself has to be bigger. So the radio waves from whatever source comes to this bowl and then is reflected into what's called a horn. That's that thing suspended by wires above the telescope. And then from there, it's directed through wires down to, I guess, what you'd call an observatory, which would consist of a lot of electronics that would figure out what that signal is doing. Now, if we put together a bunch of telescopes, either radio or optical telescopes, into a pattern, either paired with each other, in this case I think there are 21 radio telescopes all aimed at the same object, you get what's called better angular resolution. By combining their signal, it's almost as if you've created a collecting surface which is 21 times larger. So electronics, the computer power of something needed to take all of these telescopes and their data is really an incredible thing. Here's another example of some radio telescopes in Chile, and the picture in back is that of a time-lapse photograph of the stars as the Earth is rotating. Some telescopes aren't used for visible light. Instead, they're used for other parts of the electromagnetic spectrum. So this is the Chandra telescope, which collects X-rays. And you know X-rays are very, very powerful. They have a very short wavelength, very high frequency. So you're not going to have any material that can bounce or reflect the energy very well. Instead, this telescope is made so that X-rays are sort of funneled into and down to the focus of this particular telescope. Well, from that one midsection to the focus is 10 meters or 30 feet. So it's also a very, very large telescope. Here's the Hubble Space Telescope. If we have images from this particular telescope as we do in this book, you see the same picture on page 127. You know that the pictures are very crisp and clear for obvious reasons. You're above the Earth's surface, so there's no atmosphere, there's no pollution, there are no excess lights around. It's just a better place to put a visible light telescope, not because it's closer. So, what are some of the problems dealing with the Earth's atmosphere? Well, there's obviously light pollution, just as we saw on Tuesday. There's just too many lights in the area to really be able to see stars very clearly. There's also turbulence, and that's just because the air is moving. The air has different temperatures. So as it's moving, it tends to blur things in the night sky. It tends to make things twinkle. So the combination of those two effects just make it very, very hard to use a ground-based telescope. But from the Hubble Space Telescope, things are much, much clearer. This is a good diagram on page 128 that shows, first of all, the number of, or the kinds of space observatories that we have in orbit or somewhere in space that we've been able to send up and get data from. And then along the bottom, it shows the different wavelengths of light that they're collecting. So for example, and of course these arrows show which ones actually reach the ground. So something like an optical telescope would be useful because visible light actually reaches the surface. And so do radio waves. But gamma rays, X-rays, ultraviolet, infrared, they don't reach the surface of the Earth for the most part. So we need telescopes in the upper atmosphere, or I should say in space, in order to detect these waves. So the Fermi Observatory is mainly for gamma rays, and on it goes across the top. Telescopes in space solve all three problems. They don't have to worry about light pollution or turbulence. There's no atmospheric absorption of the energy, so it's just overall a better place to have a telescope. There is one thing that ground-based telescopes have done in order to improve their resolution of objects. The mirrors that are mostly used in telescopes these days have what are called adaptive optics. In other words, the mirror can change its shape very, very slightly in such a way that it compensates for the turbulence or the shakiness that the telescope would otherwise have. So the difference between A and B is incredible. You can see easily the difference between the two in terms of the angular resolution. So adaptive optics have made some telescopes much more useful here on Earth. Here's another example of Neptune with and without adaptive optics. And here's one of Jupiter's moons, Io it's called, with and without the adaptive optics. So optical telescopes have actually been improved quite a bit with the use of this technique to eliminate a lot of the turbulence or shakiness that telescopes would have here on Earth. Of course, a great spot would be the moon for an observatory, wouldn't it? There's no air, no turbulence, no light pollution. So how do telescopes help us learn about the universe? Well, we can see fainter objects in more detail. Specialized telescopes allow us to learn more than we could from visible light alone. And why do we put telescopes into space? Well, there's no atmosphere, no light pollution, no atmospheric distortion, and no atmospheric absorption of light. So it's a better place to have a telescope.